Great, thank you very much, and thank you for having me. So yeah, I'm talking about formalizing proof on unit fractions, and this is joint work with Thomas Bloom, and we did most of this between January and June this year. So what are we talking about? In late 2021, Tom Bloom proved that if you have a subset of the naturals with positive upper density, then it contains a finite subset whose sum of reciprocals is 1. And by June 2022, he and I formally verified this in the Lean theorem prover. So what I'm going to be talking about is why formally verify stuff and what is Lean. How did we end up doing this? How did it go? And then what lessons can we take from what happened here? Okay, so let me get started. What's the point of verifying maths? There's a couple of reasons. The most obvious is that you get a slightly stronger guarantee that it's correct. You can check that if you've got a long proof with many definitions or many different conditions, you can check that you haven't accidentally slipped up in some way, or you can check that you've covered every case that you think you've covered. So this is essentially a double check that the argument that you've written down does actually work. There are some more kind of pragmatic ways of looking at it. It can help you understand key ideas in isolation, or in particular, it can help students understand key ideas in isolation, because you can try and verify or understand parts of a verified proof without needing to understand the whole thing. So I mentioned for students, it can be educational in many ways as well. So if you're given a new proof, using a proof assistant can help you step through the proof and try and understand in a bit more detail what the steps are each doing. It can also be useful in practice because you notice some unneeded assumptions. This doesn't happen too often, but when it does, it's quite satisfying. You realize that a condition which you thought was necessary turned out not to be necessary. And it's sometimes easier to find this when you have a verified proof, because you can just remove an assumption and the computer tells you it's still verified, which means the assumption wasn't actually needed. Another reason is that it can help make a searchable database of mathematical results. Now, we're not quite at that stage, but there are people who are trying to make this happen actively. So if we have formally verified proofs, we also have formal versions of each statement. And what that means is it's arguably easier to search through math results to find the sort of thing you're looking for, rather than trying to rely on Google or archive searching. And then the more modern approach is to try and train an AI to find new proofs. So if we have lots of verified proofs, then potentially we can get an AI to find new ones. There are lots of people at Meta and OpenAI in particular who are actively working on this. And finally, just because it's fun. It's quite a satisfying thing to do. When you've translated a proof from what you understand in your head or what you have on paper to something where the computer says, yes, this all makes sense, it's just quite satisfying to know that it's kind of like playing a game. You've just finished a new level. Okay, so what actually is Lean? So I've talked about verifying, but Lean is the language that I use to verify maths. So I want to talk a bit about what it is and how it works. So Lean's an open source interactive proof assistant. Software like this is sometimes called an automatic theorem prover, but I think that's somewhat misleading because software like this doesn't prove your theorem for you. It instead verifies that your proof is correct. So you have to, in some way, translate your proof into computer code, Lean code specifically, and then the computer will check that every step you've made is valid. Lean's written by Leonardo de Mora and his team at Microsoft Research. Another way of looking at it is a dependently typed programming language. Now, this might not make it any clearer to some people in the audience, but in some sense, being a dependently typed programming language is very close to being an interactive proof assistant. So in theory, you can use Lean just like you use any other programming language. It's not really designed for that. It's designed for verification, but it does have this capability as well. It's worth mentioning why I like to use Lean and what I think its benefits are over other theorem provers. There are others which are quite popular. For example, Kroc and Isabelle are some of the most famous. So Kroc you may have heard of because it was used to verify the four-color theorem and also the Kepler conjecture. Isabelle also, I think, had the first verified proof of the prime number theorem. But the reason I personally prefer to use Lean is that it has an emphasis on classical maths, so you don't need to worry about exactly which variant of choice you're using, all variants of like dependent choice, global choice are treated at the same level. So you don't need to worry about the foundational axiom so much, which is nice when you're doing classical normal maths. The other slightly bigger benefit is that there's a single library mathlib. So mathlib is Lean's standard maths library, and it has a great focus on making sure every single part of it works well together. So in this library, we've got notions of topology, analysis, algebra, like modules, filters on the topological space. And all of these things, there's been great effort by the MATLAB community put into making sure these notions all work together. They're all intercompatible. And I highlighted this in particular in contrast with Isabelle, where lots of things have been formalized, but there's somewhat of a problem where one development of, say, vector spaces may not use the same definition of a vector space as another development. So the results proved by both groups may not be able to be used together, whereas Lean doesn't have this problem. It kind of creates other issues in terms of library maintaining, because it's harder to maintain this large corpus of maths. But in practice, in my opinion, it makes it easier to verify modern math, especially when you need to use tools from many different areas. So that's kind of a technical answer, but I'll try and give you a slightly more pragmatic answer by giving you a demo. So I'm going to try and prove some very basic statements just to see, so you have an idea of what Lean proofs look like, or what Lean code looks like. So here's my Lean interface. I've got the code here, and then on the right-hand side here, there'll be some messages, which I'll show in a moment. So the first line imports definitions from MATLAB. So in particular, I'm importing stuff about what topology and continuous functions are. I'm then going to declare my variables. I'm saying that X, Y, and Z are topological spaces. Technically, you can think of this as saying X, Y, Z are sets, and I'm insisting that they're all topological spaces. And then I've got functions f from x to y and g from y to z. Now, the first, most obvious thing you can prove is that the composition is continuous. And so here's what the statement looks like. I've got a lemma. I've named the lemma example 1. And I have the assumptions that f is continuous and that g is continuous. And I'm naming the assumption. So this is saying hf is the name of the assumption that f is continuous. Let me zoom in slightly, actually. And then I have hg, which is the name that g is continuous. And then I have the conclusion of the statement, which is that the composition is continuous. And we have this circle operator, which is the composition of functions. One thing worth mentioning here is that you can use Unicode operators. So I don't have to write like GOF or use LaTeX symbols. I can use Unicode symbols. And Lean makes it quite easy to type those in. So the statements look fairly familiar to what you'd write on paper. OK, so what's this proof actually doing? So as I go to the first line of the proof, on the right-hand side, it gives me the problem state, which is called the tactic state up here. And it's saying I have one goal, and I have my context and my assumptions. So my sets, they're all topological spaces, my functions, and the assumptions on them. And I have the goal to prove that the composition is continuous. The first thing I'm going to do is use the definition of continuity to figure out what continuity actually means. So I'm going to rewrite using the definition everywhere, which is what the star means. So after I do that, HF, HG, and my target have all changed. So I'll give an example of what the target says. It's saying that for every set of Z, so this is a set of elements all from the set Z, if S is an open set, then the pre-image of F by the composition is an open set. This is just what continuity means. And now I want to introduce these actual sets. So really what I'm doing here is I'm saying, let U be an open set of Z. I've changed the name to U just because I think it's easier to think of U as an open set rather than S. So now my goal state has changed. I've got two new assumptions, namely that U is a subset of Z and that U is open. Now, the first thing we might prove on paper here is say, well, if you take the preimage by G, you have an open set, and you take the preimage by F, you have an open set, and that gives you what we need. So let's name the preimage by G. Let's call it V. And after that line, I have the new thing in the goal, in the tactic state. And now I can prove it's open. So to prove, as I go in here, I've now got the new goal to prove that V is open. And once I leave this bracket, I'll have the assumption now that V is open. This is kind of, I'm pausing the proof for a second just to prove that V is open, and then I'll go back to the main proof. So to prove that V is open, we're going to use HG, because HG says that if U is open, then the preimage by G is open. I apply HG, because that's the assumption which is relevant to me. And then after I do that step, if I focus on what changes here, I've gone from saying V is open to saying U is open. But I know U is open because that's HU. It's exactly HU. And then to finish the proof, I can essentially do the same thing. I've made it a little bit shorter here. But I can essentially do the same thing with HF. So I apply HF with HV, and that finishes the goal. And we have the goals accomplished with a little emoji. So that's an example of how you might prove something in Lean. Now, this is a fairly simple example, so it might be worrying that it's got such a long proof. But what happens in practice is I've made this example kind of artificially long for the sake of demonstration. And there are much shorter ways of doing this. So for example, I think if I were to write this, that would work as well. But really what happens in practice is that you don't want to prove this yourself because it should be a standard result. So I can do library search and ask Lean to find the proof for me. And it finds the result in the library, which is that the composition of continuous functions is continuous. So here I'm using mathlib to save myself some work. Okay, so then I have another example here, which I'll go through much more quickly, which is that the composition of surjective functions is surjective. So again, I'm going to rewrite using what surjectivity means. It means exactly what you expect it means. Then I take my arbitrary element Z. Now, using HG, I'm going to pick the element in Y, which corresponds to Z under F. And that's what this obtain tactic does. So you'll have noticed that on each line, I'm starting it with some keyword, which is essentially a proof step. Maybe introducing a variable, rewriting with a definition. RW stands for rewrite. Obtain will take out the element from an existential. So here I've got Z, and I'm taking out Y to get there with the assumption that GY is Z. I do the same thing to get an element X. And now to prove this, I'm going to use X, because that's the element I need to pick. And from there, I can rewrite based on what function composition is, and then end the proof. So that's what that looks like. And again, there is a short proof, but I wanted to give an actual example. Now, one thing which might stand out to you here is my first example was on topological spaces. This one isn't on topological spaces. And Lean can actually figure that out. So if I use this lint command here, it checks all of the lemmas I've made. And it says that there are unused arguments. In particular, in example 2, the argument that X is a topological space was unused. Similarly, that Y is a topological space and that Z is a topological space. So it can tell me that in this example, it never mattered for them to be topological spaces, which makes sense. And this is kind of, again, a baby example, but you can see how Lean can be useful to help detect unnecessary assumptions. Okay, now the final example I wanted to give you is just for prime numbers. So I'm going to add an import which tells Lean what the definition of prime numbers are. And then here's my example. I'm saying that for every natural, there exists a natural P, which is larger and is prime. So the main reason I wanted to highlight this example is that I've used the symbols for all and natural numbers. And it has an easy proof, or rather the proof is in mathlib already, so I don't need to work it out. But this is a nice feature of Lean, which is that I can write things in a more human style way. I don't have to write nat or any different symbols for all. It just looks like what you expect it to look like. Okay, cool. So that's
Can I ask you a question?
Yeah, absolutely.
So I was wondering, are you showing us like a sort of debug state of Lean, or is this what actually using Lean every day looks like? As you constantly look at this tactic state and see where you're going? Or
Yeah, this is what it actually looks like. This isn't any special debug state. This is actually how you do proof things.
Okay. Okay.
So yeah, I have kind of expanded the example to make it clearer what's happening. But in practice, this is what it looks like. You've got this tactic state on the side, which tells you where you're at in your proof. And most of the time when you are proving things, you'll use this a lot to figure out where you've got to.
So what does it look like when you write down a proof that doesn't work?
That's a really good question. So let's just say I haven't figured out that I need to use, I don't know why g of y is z for whatever reason. Then I've got one goal left and it can't figure it out. So instead of giving me the goals accomplished, it says tactic failed, there are unsolved goals, because there's something I didn't finish proving. This would happen more commonly if I missed an assumption. So if I used some lemma which needed to assume that x is positive or something, and I didn't prove that x is positive, it'll tell me there are unsolved goals, and it would say the unsolved goal is that x is positive, because I missed out that case.
I see. Do you ever have runtime situations where like you've written down quite a complicated proof and it takes a long time to even figure out whether it works?
Yes.
Okay.
That definitely happens. The usual fix for that is just to break your proof up into smaller parts.
Yeah.
And because they run independently of each other, then you don't get the runtime error, essentially. It can still end up taking a while. And so I mentioned MathLib is this big corpus of maths. To compile, to check all of MathLib takes about 6 or 7 hours.
Right.
It happens in parallel, and in practice, we have some ways of speeding up and parallelizing and everything. But if you were just to run it on one computer without using any tricks, it would just take 7 hours.
To compile it. Is that like
to compile to, as in to check everything's correct. Cool.
We have a question in chat. Kevin Hughes asks about the meaning of colons. Colons seem to have multiple meanings. What do these do in general?
Okay, so I'm looking through the examples of colons I've had here. So there's a colon there and there's colons here. These are actually all the same meaning. All of these colons are saying the left-hand side is a name and the right-hand side is its type. So here I'm saying f is the name of something and f is a function from x to y. Here hf is the name for a proof that f is continuous. So this is a type declaration, if that is any clearer. So hf has type continuous f, meaning it's a proof that f is continuous. I think that's the same for every example of colons I have here, including this one. So I could also put colons around this, and it's saying for every n which has type natural numbers, i.e. for every natural number, similarly for this one. And then the colon equals is treated as its own separate symbol. So that's that's just treated as a different symbol. Cool.
Thank you.
Okay. So let's talk more about formalized maths in general. Combinatorics has been formalized before. There's lots of stuff. For example, Sperner's theorem on anti-chains has been formalized in many different systems. Lots of kind of elementary stuff, like the cardinality of the power set of a finite set, has been done. Most of it's elementary, but there's a very important exception, which is the cap set proof. So this was the result from a couple of years ago, solving the cap set problem or giving a better upper bound. And this was formalized in Lean, I think I think maybe a year after it was first announced. So this is the proof which uses a polynomial method to deduce something about subsets of f3 to the n which don't have arithmetic progressions of length 3. In general, most of the maths being formalized is old. I say most, there are some exceptions, which I'll come on to in a sec, but in general, most of the stuff is relatively old maths, and by that I mean pre-1980s. So as a kind of extreme example, there's some analysis which is actively being formalized, complex analysis, not elementary. There's lots of algebra being formalized, stuff like Silov's theorems. That's been lots of the focus of most formalization communities so far. And this makes sense because if you're trying to formalize new maths, you need to have a good understanding of old maths first. But there are some fairly big exceptions to this. For example, the four-color theorem, the Kepler conjecture, which were done in, I think, both in Coq, and then perfectoid space and condensed sets, which are modern tools in algebraic geometry, which have been done in Lean, and homotopy type theory, which is very modern and is been done a lot in Agda. So there are exceptions, but throughout all of these examples, there's not much additive combinatorics, which is really what I'm here to talk about and what I think is more interesting. And so when I came across theorem provers, the main thing I wanted to formalize was combinatorics, because that's the sort of math I'm interested in. It seems like not a whole lot has been done except for this single example of the cap set proof. Okay, so that's kind of the background of why I wanted to formalize combinatorics in the first place. And I want to give you a quick timeline because I think it's interesting. So in early 2019, I took Tom Bloom's Part 3 Cambridge Master's course on analytic number theory. Later that year, I started learning Lean, and I did some extremal combinatorics, stuff like Kruskal-Castaner, Sperner's theorem, limb inequality, stuff like that. In late 2020, Tom Bloom mentioned the density problem that I mentioned earlier. He mentioned that it's open on a Twitter post. In late 2021, Yael Gilias, who was an intern of mine, and I formalized Roth's theorem, again on arithmetic regressions of length 3. And then a bit later, Tom Bloom asked on Twitter if analytic number theory had been done in Lean. So I saw this post, and since I'd already done a bit of additive combinatorics in Lean before, I reached out because I'd already met him, and I thought maybe it'd be interesting to see if there's, because this was just after he'd solved the density problem, and so we discussed whether it'd be feasible to formalize it. So that's kind of how this ended up starting to happen. Okay, I want to give you a bit more of an idea of what additive combinatorics has been done. So I mentioned the cap set problem, which was done before I started doing Lean. But after I started, there are a bunch of more examples, some of which were by me, some by Yael Gilias, and some by both. So this is a version of the sum product inequality. Hopefully this should be fairly readable. So a lemma saying that if A is a finite set of real numbers, then I have the bound that the cardinality of the finite set raised to the 5/4 power is less than or equal to the max of the sum set and the product set, with the constant 1/5 at the front. Usually this is stated with just there exists a constant, but the proof ended up giving an explicit constant, so I wrote it down. Now 5/4 isn't the best exponent, as I'm sure most people here know, but it's the one which I found convenient to formalize. And this is a nice example because so the cap set problem is very algebraic. It uses the polynomial method. Some product results typically are quite geometric, including this one. So this is this needs a bit of geometry to do the additive combinatorics formalized. And then Sem-Radius regularity lemma, which I mentioned earlier with Roth's theorem. This one uses a bit of real analysis, but mostly lots of statements about inequalities of real numbers, and lots of dealing with finite sums and partitions. So that's all stuff we can do in Lean. Also counterexamples, not just theorem statements. So Barron's example of a large set without any arithmetic regressions in it I also formalized that one. And then stuff just on pure sum sets, like the Plunker-Ruser inequality, has been done by Yael Gilias. So that's kind of a broad idea of the different sorts of things that we can formalize. And I think it's lots of these are maybe arguably quite simple, but they kind of demonstrate a breadth of the sorts of arguments which we can formalize. Okay, so what about this proof? So this proof is quite a bit longer than any of the, or most of the other ones I've mentioned before. Most of the other additive combinatorics ones I've mentioned before, I should say. It uses a combination of analytic number theory, Fourier analysis, and combinatorial reasoning. And because it needs all of these, we need to formalize all of those as well. In particular, we need to formalize every prerequisite paper and result from this main paper we're trying to formalize. The other prerequisite which are important is that both Tom and I need to be able to use Lean. I did before the project started, but Tom didn't. And so part of the project was also helping Tom learn Lean. And then the other way around, Lean needs to know the basics. So as an example of this, the proof uses prime powers a lot. And MathLib helps. It's got definitions of primes. It's got definitions of real numbers, all the basic stuff like that. but it didn't have prime powers. So part of this also a strange omission, but that's something which we also need to add. And yeah, like I said, Lean's MATLAB helps a lot, but you also need to know how to use it in these contexts. So part of some of the analytic estimates need to work with integrals. And before this project, I hadn't done any integration theory in MATLAB. So there's also kind of this getting used to how different areas of the library work. Okay, so now I'm going to try and give you some more examples of the sorts of prerequisites which we try to do and how they work. So at the bottom here, sigma is the number of divisors function. Oh, sorry, sigma 0 is the number of divisors function. And then here's the weak divisors bound. So in words, this would be that the number of divisors is less than n to the epsilon for any positive epsilon and sufficiently large n. Now, I was very sloppy with the quantifiers there, which I absolutely can't be in Lean. So what this actually says is for every epsilon and with epsilon positive, and I have this for all f, which is notation for sufficiently large f, sufficiently large n, sorry. And yeah, I won't explain too much about this notation. It will show up a lot, but in every case, this part, if it says for all f in at top, it's saying for sufficiently large n. So for sufficiently large n, the inequality that we expect to be true is true. Now, this is actually an example of where I am using colons differently. The main thing is that here I've said n is a natural number, and here I've said that n is a real number. To do this exponentiation, because it's to the power of a real number, Lean doesn't like if I want to take a natural number to the power of a real number. Instead, it wants me to convert the natural number into a real number and then take the exponentiation. So it's kind of annoying, but it does need to be included in the statement for Lean to understand what I mean. I've included it here just to make that point of this is the sort of precision you sometimes need to make. In general, I'll try to omit it where necessary. So for example, in the earlier one, I've omitted some of those. But that's the sort of thing which needs to be specified. So this is a weak version of divisor bound. There are stronger ones which exist, which we did prove. But what I want to highlight is the way in which we proved it was instead proving a bound which works for any k and has a slightly weird looking right-hand side. So this is n to the 1 over k times k to the power of 2 to the k. Sorry, k, yeah, no, I said that right. K to the power of 2 to the k. And if you inspect the normal proof of this sort of statement, it would prove something like this, but then you choose a very specific value of k. I think something like, or something on the order of 1 over log n. And it turns out in practice in Lean to separate these two concerns out, to prove something that works for every k, and then to pick the right choice of k later. So that's why we proved this version, and then use it to deduce the actually interesting divisor bounds that you might be more familiar with. Other things we have to formalize are Chebyshev estimates. So psi here is the usual Chebyshev function, sum of long angles. And again, the second result is the familiar upper bound, which is saying that as n tends to infinity, so infinity is what the at top represents, the Chebyshev function is big O of the identity function. Now, again, this looks a bit unfamiliar, but hopefully you can trust me that is O means what I'm claiming it means. Actually, since we did the project, the notation's changed to make it look nicer. But it still means the same thing, that psi is big O of the identity function. And then here's a more explicit version of that, which is saying that if c is a constant greater than log 2, then there exists a constant capital C, so that psi of x is less than or equal to this linear expression. So this is a more explicit way of saying the same thing. And again, it's easier to prove this slightly more explicit version and then deduce the usual big O version. Okay, and then here's one more example. So this is not one which we actually needed for the project. But I realized at some point that I'd done all the prerequisites to prove this, so I might as well prove it. So this is a theorem which says that the lim sup of this particular thing involving the divisor function is log 2. And this is what the statement looks like in Lean. And again, I think it looks very similar to what you're used to reading. So what I want to highlight here is that lean proofs, lean statements look very familiar. The other thing is, in lean, we don't have the prime number theorem. And some authors seem to claim that this proof needs the prime number theorem. But the proof in Hardy-Wright doesn't actually need the prime number theorem, and so that's the one which we formalized. Okay, so then one more thing I want to highlight is how did we actually do this? So the proof was originally a 17, 18 page long paper. And so the main step, the first step we did essentially was breaking it down into a number of smaller lemmas. So I mentioned earlier that it's useful to separate out different lemmas, both for speed, like Sean mentioned, but also just to separate concerns. And so here's the graph of the things we had to prove. These two at the bottom, density theorem and log density theorem, are the two main results of the paper. Density theorem is the one I mentioned earlier, and log density is the quantitative version of it. And then these are the prerequisites needed for that statement. The colors here, the green background means something that had been formalized. And then blue background means it's been stated but not formalized. And white background means there's no version of it in lean. This is a picture I took at late January. So this is after some progress had been made, but not much. I should also mention that this blueprint was designed for a different project, and I adapted it for this project. Okay, so that's kind of practically the way we went about it. And then essentially, he and I tried to make as many things green as possible. Okay, so the main upshot, the proof was correct. We succeeded. We now have a formalized proof of the statement. And I've written it here. Hopefully, it looks very similar to the original statement I wrote at the beginning. So I've got a set of naturals A. I have that it has positive upper density, and I've named the assumption. And then the conclusion is that there exists a finite subset of the naturals, which is a subset of A. And as I sum n and s, 1 over n is 1. Now, again, I've done this extra thing here, which is the colon Q. This time it is important that it's necessary. And the reason is that if I were to omit the colon Q, lean would try and think that the 1 over n is a natural number. And so it would try and do 1 over n as natural division. And natural division would be 1 over 1 is 1, but 1 over 2, 3, 4, anything else will be 0. So the statement wouldn't mean what we think it means. In particular, it would be false, because you could just have, the set of all the naturals above 2. Then there's no finite subset whose sum would be 1 under that definition. So what's important here is that even if I'm claiming the proof is correct, there is still kind of an extra step of you need to trust that all my definitions are correct. You need to trust that what I've stated is what I'm claiming to have stated. So it would be completely unfair for me to say, this is 100% guaranteed that the theorem is true. What I'm instead claiming is that under the definitions that are in MathLib that have been checked by other people, and if you assume that lean is sound and that you can't easily prove false, then lean has verified this theorem. So yeah, there is some extra work to check that upper density means what I say it does. The rationals aren't something weird. Maybe I define the naturals to be an empty set, and so this is a vacuous statement in some other way. So there is still a bit of extra work here. But the main thing to highlight is that the extra work that you need to do there is different and arguably easier than the work you need to do to read the paper. So if you're going through an 18-page long brand new paper, you need to understand the full proof. Whereas if you do trust the definitions, then there's no extra work to check that the proof is correct, because lean has verified that all the steps of the proof line up. And because I showed the picture earlier of the graph, let me show you the graph at the end, which looks like this. So everything is green. Yeah, everything's green. And so here are the two main statements, and then density theorem is the one which I just highlighted there. Okay. Actually, let me quickly highlight some other examples so you can see the sorts of statements we have here. So Merton's primes is Merton's estimate for prime numbers. and it says that there exists a constant c, so that if you take the sum over primes, you have this behavior. And so this is one of the things which we needed to formalize. And then there's some slightly more technical lemmas. So this one here, is a version of one of the theorems on the paper. I'll talk about this in more example in more detail in a moment. But this is the conclusion of all the Fourier analysis in the paper, essentially. And this is something which we have to convert to lean and then formalize. Okay, oh yeah, I showed the blueprint now. So along the way, we ended up proving a whole bunch of these important prerequisites, which were new to both lean and MATLAB. For example, prime powers. Stuff like von Mangold function is now in MATLAB and it wasn't there before. And then there's stuff that we haven't yet put in MATLAB, but wasn't known to lean before. Yeah, stuff like the integral of x to the r from 0 to infinity, or from 1 to infinity. That was missing from MATLAB, and it's now been done for this. The other thing which I want to highlight is that Tom Bloom learned lean for this. When we started in December or so, he didn't know any lean. And so like in January, February, I was writing most of the code. But then as it got to the end, he was writing more code than me. He formalized lots of parts of his own proof. And so even though I did work on this project, there are still bits of the proof I don't understand because I didn't work on formalizing those parts. To the best of our knowledge, this is the first formalized proof of an Erdős conjecture, and I'm pretty sure it's the first formalized. If it's not, then it's certainly the one which has been open the longest before it was solved. It's also, we think, the first instance of the Hardy-Littlewood cycle method, which was formalized. And so this was part of the Fourier analysis that we needed to do. So one thing which is worth talking about is how much did we need to modify the proof on paper. So I mentioned converting it to this blueprint, and most of that was essentially just breaking things up from the proof on paper, but there weren't really any mathematical changes there. But there were some mathematical changes which are made instead. For example, iteration processes, which are relatively common. It's a lot easier to formalize them if you reframe those in induction arguments. And if you think about it, technically that's what you're doing anyway, but writing it explicitly as an induction makes it just easier in practice to formalize. You need to be very precise about what integers and reals are. So I kind of highlighted this earlier of converting from naturals to reals, from naturals to rationals. It's something which you need to take care of in a way which might be surprising. Especially in combinatorics literature I've read, there seems to be a habit, which is sometimes explicitly mentioned, of treating large real numbers as if they're integers. And that's not really something you can do in lean. The other thing is that some constants need to change. Now, this is essentially insignificant. It's usually the constant in front of a big O, or like the powers in, not the power, sorry, the coefficients in terms of in front of an expression. They sometimes need to change. Most of the time, it's actually because of this issue of pretending that large reals are naturals. And this happened in my experience a lot throughout combinatorics, where when formalizing something, I need to adjust the constant slightly. But I think it's completely unfair to call this an error in the proof, because all of the key ideas were still the same. You just need to change some of the details in a way which is a completely minor modification. And so yeah, I've mentioned this a few times, that it's really important to break down statements into smaller parts. This is arguably useful outside of formalization, just to understand exactly what you're doing in each argument, but it's essentially necessary for this purpose. I'll talk a bit more about what was difficult. One thing I personally found quite difficult was working with infinite sums. So one thing, I mentioned this earlier, of the sum of 1 over p up to a fixed point, comparing the one for prime powers and primes. I found proving this with the appropriate error term, I think, the most difficult thing of the project. And I think the most difficult thing I've formalized. And now it's certainly not the most advanced thing I've formalized. It's not really the most difficult proof. My best guess of why it was so difficult is that I hadn't worked with infinite sums in lean before. I should say, by the way, I've written down a finite sum and I'm talking about infinite sums. But the way this proof usually goes is by looking at the tail part instead of the early part. So the proof usually goes via infinite sums of this. And so what I ended up doing was, with Tom's help, reformulating the proof to only use finite sums, and then it was fairly easy. So I think the main reason this was difficult is that I just was fairly unfamiliar with infinite sums. There's an issue again of switching between naturals, integers, rationals, reals. This is something which I think Tom found particularly annoying. It's become easier. Maybe 2-3 years ago this was a lot harder. It's now become easier, but it still happens fairly often. It's still a little bit annoying. I'll come back to that question after I finish the slide, if that's okay. And then some statements look a bit strange. I'll give an example in a sec, but let me talk about this question first. At a few points so far, you start with a number that's in one set and consider it inside a bigger set. Can lean go the other way around? To be more precise, can lean verify that an integer coming out of some calculation, which you know priori is, say, real, is actually an integer? Yes, you can. The usual way of stating this is to say, let's say I've got my real number x. Then the way I'd state this is to say there exists a y, which is an integer, which has type int, it's genuinely an integer, and y is equal to x. So if I turn y back into a real number, it's equal to x. So that's the way I'd state that. I don't think that happened in this project, but it has definitely happened. So that's the way you'd usually state it, by kind of, you are going the other way around, but you kind of view it as if you're going in the same direction of going into the bigger sets. So yeah, it's absolutely possible to do that. Yeah. So yeah, I mentioned this thing of switching between these sets. And there are tactics which make this a bit easier. So for example, rewrite earlier was a tactic which lets me convert one term to another term if I know they're equal. And I have other tactics, which are called the norm cast family, which make these switches a bit easier. But it's still kind of awkward in practice anyway. And then finally, some statements look a bit strange. So I'll give you another example. This is the density, sorry, this is the quantitative version of the statement. So I think this was theorem 3 from the paper, and the earlier version was theorem 2 from the paper. If I can quickly go back to this. This is the statement I wrote earlier, and then this is the statement I'm writing now. So instead of talking about positive upper density, I've got a finite set now up to n. And the theorem is that if the reciprocal sum is larger than a particular constant, there is a finite subset whose sum is 1. So that's what the maths statement looks like. But here's what the lean statement looks like, and it looks a little bit uglier. So again, I have this sufficiently large n thing. Now you can kind of adjust constants to make it work for small n as well, but that's not particularly interesting, so you might as well just assume n is large. And then I have this a subset ICCIN, which looks a bit strange, but this is notation for the closed interval from 1 to n. So interval closed, closed. That's what I'm writing here. And then I have this thing with the q again. There's also the inequality looks the wrong way around. I've put it as a less than instead of the greater than, which I had before. For various reasons, MATLAB just prefers less than symbols rather than greater than symbols. It makes kind of finding proofs automatically easier. So it's a bit weird to get used to, but with a bit of practice, it works, and it's obviously equivalent. But it just means some statements look a bit unfamiliar. Okay. So yeah, this is some stuff I had to add to MATLAB, stuff like prime powers. There were some basic analytic number theory things we needed. So like the Chebyshev estimates I mentioned, divisor bound estimates. Fortunately, we didn't need the prime number theorem. And the reason I particularly highlight this is I think the project would have been a fair bit harder if it did need the prime number theorem. This is partially because when we started, there wasn't much complex analysis in Lean, which would make the complex analysis proofs of the prime number theorem nice. And we could have done the elementary proof of prime, or one of the elementary proofs of the prime number theorem, but that would also just be extra time and it would be harder than the stuff which we did do. So it's possible, it just would have made it take longer. The other thing which is a bit annoying about MATLAB is that some lemmas are too general, which is a slightly strange thing to say because you usually expect generality to be a good thing. But I mean this in the sense of, in practice, if you're new to a particular area of MATLAB and you're trying to find a very concrete lemma, it's usually stated in the most general way possible. And so it might not be obvious that what you're looking for and the lemma you found are the same thing. So this happened to Tom a lot with the finite sum stuff. So in almost everything, we're talking about finite sums of real numbers or finite sums of rational numbers. But the MATLAB lemmas are often stated in terms of additive commutative monoids. And so you need to every time make the jump that the reals are an additive commutative monoid, which they obviously are, and so it's completely fine. But you need to know where to look. And Thomas says in the chat, this is one of the most frustrating aspects for me. This also has a consequence for the prime number theorem stuff. For contour integration, you can kind of formalize it in the undergraduate way that you'd normally see complex analysis, but the community wanted to get the most general theory of integration possible. So the version we have for integration now proves like Green's theorem, Stokes' theorem, and statements of complex integration, so contour integration, all in the same way by unifying them in a very clever way. But what that means is it's just harder to do, and so it takes a bit longer to end up in MATLAB. Now, with all that said, I still think it's the right decision for MATLAB to work in this extra generality, because it means you don't need to duplicate results. It means it's easier to maintain, so you don't have multiple versions. So I think it's definitely the right choice that the MATLAB community has made. I just want to highlight that in practice, for doing some sorts of math, it can just be annoying. Another thing is growth of large functions. So lots of the times we had stuff like, say, log n is less than log n, or really a billion times log n is less than log n for sufficiently large n. And that's the sort of thing which you'd just be very happy to write down on paper. But proving that in Lean happened very often. Even though most of the proofs are fairly short, it happens often enough to be annoying. So that's something where it would be nice if Lean's automation would make that part easier. Okay, so now I'm going to try and give you some examples of non-trivial statements, because the ones I gave earlier were relatively simple. So this is one of the main technical lemmas from the paper. So this is proposition 2. This is a direct screenshot from the paper. The proof of this takes up an entire section, the Fourier analysis section of the paper, and it's one long 3-page LaTeX proof. It's a pretty technical statement, so I won't need to go through it. But that's what it originally was in the paper. The version on the right is the version from the blueprint. So it's been essentially reorganized to fit in the blueprint. Now, some parts look the same, so condition 1 is exactly the same. 2 is the same, just with different notation. But there's some changes. For example, there's a new parameter t here, which essentially makes it a bit easier. So instead of this n to the 3/4, we've changed it to t, just to make that part of the proof a bit easier. And then that's also why there's a t factor here. There's also the change that this cm here, k is less than or equal to cm. In the blueprint, we've got an explicit number 1/64 instead of c. But c still plays a role here and here. So the c is still used, but this constant didn't actually need to be the same as this constant. So we can just change this 1/64. And in the blueprint, it's a few paragraphs of proof, and it's got about 20 earlier prerequisites, which is essentially splitting up the 3 pages into smaller lemmas, which makes the actual proof of this a lot shorter. It's only a few paragraphs. And then, so on the left, I've got the same thing. On the right, I've got the Lean version of the statement. The proof is about 80 lines, but there's about 100 lemmas which come before it, which are essentially translations of these 20 earlier things. And the file this is in was the Fourier analysis file. And you can see this is on line 1500. So it's about 1500 lines of stuff which has come before this to be able to prove this main statement. So the 3 pages from earlier has gone to about 1500 lines. Now, it's probably possible to reduce those lines by quite a lot. Some of them are just things which are missing from MATLAB. Some of the proofs are just unnecessarily long. But this is how it is right now. We didn't attempt to try and shorten any of the Lean proofs or anything. The other thing I want to highlight is that the 1/64 has changed to 1/192. And that's just because it turned out to be easier to formalize it with a weaker bound there. It's just an example of changing constants in a completely irrelevant way to the application to this lemma, but we just make it a bit easier in practice. Similarly for the 16 here, so I've got a min of L times K squared, so that's this term. Just put a 16 at the bottom. It makes no difference because there's a constant anyway, but it was just easier in practice to add these extra things. Now this one might look suspiciously short, and that's because of this good condition here. Good condition is an abbreviation for a definition elsewhere, which is stating all of 4. So this one line is actually doing all of 4, all of 0.4 here. So yeah, that's what one of the more technical lemmas look like. Now, this is not a lemma I don't think will be useful directly to anything else. It's useful in the paper, and maybe some of the ideas will be useful elsewhere. But the exact statement, I don't think it's worth me going through or anything. But here's an example of the sorts of thing which show up in math, and here's what the Lean statement looks like. Okay, so those are some example statements. Here are some example proofs. The first one I'm going to give you is kind of a really bad example, in the sense of this is, I think, one of the worst looking examples. I'll show some nicer ones in a second. But here's an example of the sort of growth of large functions things I mentioned. So the statement here is saying 2 times log of log 2n ceiling squared is less than 1/500 times log n. And this is the sort of thing where on paper you just say, well, it's obviously smaller. I've got 3 logs, even though there's a square, it's just obviously smaller. But the proof, I think, is about 80 lines of this. And it's not a particularly nice proof. And I've even simplified it to make it look nicer. It looks worse than this. And I've cut off stuff at the bottom as well. So this is one of the areas where I don't know how it would be actually implemented, but if there's a way of automating this sort of proof, it would be amazing. As an example, I take my earlier statement back. Thomas says this was the most frustrating aspect. So, and as an example, there's this helper or this have statement halfway through the proof here, which is saying that 0 as a real number is less than 1500. And the proof of this is just one line. There's this clever technique called norm num, which can prove basic things about explicit numerals. Before norm num existed, the proof of just this part would be at least a few lines, maybe more, and it wouldn't be trivial to find. And so we now have norm num, which makes this incredibly easy. You don't need to spend any time worrying about it. So hopefully in the future, this sort of statement will have a one-line proof as well, so that no one else has to go through this sort of thing, because it's not very pleasant. Okay, so that's the worst example. Let me show you some slightly nicer examples. So here's a statement which okay. Here's a statement which was needed in the proof. Now it's a fairly simple statement. I've got a real number x. I'm saying it's between 0 and 1/2, and then I'm trying to show that 2x is less than or equal to sine times x. And the proof is a lot simpler. This is the actual Lean proof, by the way. I haven't been able to cheat or anything this time. And I won't be able to step through exactly what the steps are doing, but it's only 6 lines and they're all fairly nice. This linearith here, I think it's showing that 0 is less than 1/2. So just like earlier, while norm num is really good with explicit numeral calculations, showing that 0 is less than 1/2 is also something which you do need to prove. But that's very easy. I just write linearith and stop worrying about it. And then from that, I can prove this bound, which was one of the lemmas from the blueprint, which is this bound on cos. So cos pi x is less than or equal to this exponential. And this ended up being very useful in the circle method, because you can convert from, we start off with a sum of causes, you rearrange it to be a product of causes, and then you get a product of exponentials, which is then very nice to deal with. So this is what the proof looks like, and it uses Jordan apply here. So again, I can step through the proof now. I won't do it in too much detail, but I start off by writing this part, and then I do some transitivity steps to end up with the result. And then this is something which we didn't notice in the blueprint, but turned out to be useful in practice, which is that what you actually do is use this with negative x as well, which is completely fine because you can just take absolute value and it's the same thing. But it's useful just to have that as a separate statement. And this proof, I will step through. So I start off by using this statement LE total, which says that either x is greater than or equal to 0 or it's less than or equal to 0. And so I now have two cases after this. I've got two goals, it says here, one of which is the statement when x is negative, one of which is the statement when x is not negative. I have to prove the two things. And they're both fairly simple. I rearrange the abs, I rearrange, and then I use the bound from earlier. So it's a fairly simple statement, but this is the sort of proofs which come up in practice. And now a slightly less trivial statement. So this is the bound. So in part of the circle method, we have bounds on the minor and major arcs. We split the minor arc in this particular case, you split it up into two parts, minor arc 1 and minor arc 2. And this is the bound on the sum on minor arc 1. So again, I've got this for sufficiently large n. Then for every k, m, t, and all these constants. Ooh, that's not good. And one thing this enforces is that n can't depend on a. So when you're dealing with sufficiently large things, it's quite easy to get like quantifiers mixed up, especially for students. I know I've made this mistake many times. But in Lean, because the a has come after the n, you can't make that error either when you're proving or using this statement. And so the conclusion says that as you sum h over the minor arcs of this function, you get less than 1/8. This proof looks a bit less nice than the other ones, but hopefully still better than the horrible one I mentioned earlier. And it uses the same keywords of I have something, and then it suffices. I use norm num. It's the same obtain rewrite tricks from earlier. So it's really all of those techniques together with more lemmas, sorry, from the library, which fit together to prove this. And then this is on line 1000. So this bunch of stuff will just come before this as well. Okay, so that's some examples. And so what's the takeaway from this? So the main thing is that very recent additive combinatorics is very accessible to verify. So this is a result from late 2021, and by mid 2022, we'd completely formally verified it. So this is in contrast to what some people are working on, where you're formalizing to very old results. This is incredibly new. Now, in this, we did check everything. There weren't any assumptions which we didn't bother proving. We had to do all the prerequisites. But if you don't have that requirement, it's even easier, because you can state the prime number theorem just as an assumption, and then prove your result depending on the prime number theorem. So in that case, you don't need to worry about all the prerequisites. You have the freedom to just check the part of your proof which you're not completely sure about. And then it will either highlight the cases which you've missed, or tell you that you haven't missed the case. So here are some things which are actively being worked on, mostly by Yale Dilias, who I mentioned earlier. They're working on Feynman's theorem in the finite fields case, and Knies's theorem on some sets in additive groups, in abelian groups. And the other thing I need to mention is that MATLAB is rapidly growing and improving. So I mentioned that we have norm num and norm cast to get around some of the annoyances of proving simple things about numerals. So hopefully all of the problems I've mentioned today will go away fairly soon anyway. And the prerequisites which we've proved, when they hit MATLAB, you won't have to prove them either. So we're getting even closer to the step where you can formalize the paper you wrote yesterday. There are still some things which are tricky though. So prime number theorem, Dirichlet's theorem aren't in Lean. Dirichlet's theorem is on arithmetic regressions, I should say, is in MetaMath, and there was a translator from MetaMath to Lean, but it gives you a different definition of the prime numbers for essentially weird technical reasons. But what I want to highlight is right now we can't translate between different theorem proving languages. The prime number theorem has been done twice in Isabelle, but again, we can't convert that directly into a Lean proof. The other thing is that we don't have planar graphs yet. We have simple graphs. I think the thing with planar graphs is that there's many possible definitions, and getting them all to be equivalent and show they're equivalent is somewhat tricky. And so what this means is that some stuff like crossing number inequalities for some products might be a bit difficult. Although I think certainly the first two of these would be fairly good as if you have like a team of undergraduates who have a summer project. I think either or both of these would be completely accessible. The other thing which is tough is small number computations. So by that, I mean, if you have to check a result by doing explicit calculation or checking a lot of primes. That sort of thing is quite difficult. Lean is very good at reasoning. It's not so good at computing. So essentially, the summary of almost everything I've said is that I think Lean is a very good tool to check parts of your additive combinatorics proof. Trying to check all of the proof is feasible, but might be difficult. But if there's a particular part which you're anxious about, then I think Lean is a very good option for that, almost regardless of what sort of tools you need in that proof. Okay, so as I finish, let me talk quickly about where you can start. So here's my project website, which has the blueprint and some like details. You can see the graph and you can see the proofs that we have, and you can see the code. If you want to get started learning Lean, this is Kevin Buzz's natural number game, which leads you through some of the most basic tactics and gets you to prove some basic things about natural numbers. And then there's Zulip chat, which is probably the best way if you have questions about Lean, which is essentially a Lean research environment where people discuss working on Lean and using it to formalize maths. And finally, you can reach out to me if you want to discuss formalizing your paper. I need to give thanks to Patrick Masso, who developed most of the architecture for the blueprint setup, Eric Rodriguez, who helped push the project over the finish line, and the MATLAB community for making MATLAB and doing so many prerequisites that I didn't need to do. And thank you for listening. I'd be very happy to open discussion and take any questions.